Welcome everyone. Today we will be exploring one of the most powerful techniques in modern AI, which is reinforcement learning and its human feedback driven extension called as reinforcement learning from human feedback. Reinforcement learning is a framework where an agent interacts with an environment to learn optimal decision-making strategies. Unlike traditional supervised learning, where models learn from elaborate data, RL allows AI to learn by trial and error, receiving rewards for good decisions and penalties for bad ones. This technique has led to breakthroughs in fields like autonomous driving, game AI, robotics, and personalized recommendations. But more recently, RLHF has become a crucial method in training AI models like ChatGPT. So what exactly is RLHF? Instead of relying only on predefined real functions, RLHF incorporates human feedback into the learning process. This makes AI responses more natural, aligned with human preferences, and contextually relevant. Today, we'll explore how reinforcement learning works, its underlying mechanics, and how RLHF is shaping the future of AI. Before diving deeper, let's first break down the fundamental components of reinforcement learning. An RL system consists of the following key elements. First, agents. The AI system that learns by interacting with the environment. Second part is environments, the world in which the agent operates. Third part is states, which is called as S, and it is a representation of the environment at a given time. Fourth part is an action, and this is the choices that agent can make. Finally, reward is a numerical signal that tells the agent how good or bad an action was. This interaction is formalized as a Markov decision process, where the agent learns a policy that maximizes the expected future reward. The goal of LL is to find the optimal sequence of actions that yield the highest possible cumulative reward. Unlike supervised learning, where we have reliability data, LL is based on exploration and exploitation, balancing the need to try new actions while maximizing rewards from known actions. In order to make optimal decisions, an RL agent needs a policy and a value function to evaluate the potential outcomes of its actions. A policy defines how the agent selects actions. It can be deterministic, which is always choosing the same action for a given state, or stochastic, which is selecting actions based on probabilities. A value function estimates the total expected reward from being in a given state. A Q-value function goes a step further and estimates the expected reward of taking a specific action in a given state. By continuously updating these values through the trial and error, the agent gradually learns the most effective strategy for maximizing its long-term reward. The ability to learn from rewards rather than explicit supervision is what makes reinforcement learning so powerful. There are two major categories of reinforcement learning algorithms. First, value-based RL. This approach estimates the value of different states or actions to make optimal decisions. The most well-known example is Q-learning, where an agent builds a Q table to keep track of expected rewards for different actions. Another thing is deep Q networks, which extend Q-learning by using neural networks to approximate Q values, allowing the model to handle complex environments. Second one is policy-based RL. Instead of estimating values, these methods learn the policy directly by adjusting probabilities of actions through trial and error. First part is policy gradient, which is optimized policies based on expected rewards. Other part is proximal policy optimization, which we'll discuss next, improves the stability of policy learning. Each approach has its strengths. Value-based methods work well in discrete action spaces, while policy-based methods are more effective for continuous control tasks such as robotics. One of the most widely used policy optimization techniques in LR today is proximal policy optimization, which is called as PPO. In standard policy gradient method, the model directly optimizes the policy by reinforcing actions that lead to higher rewards. However, traditional policy gradient updates can be unstable, sometimes making drastic changes that lead to poor performance. PPO solves this by using a clipping mechanism to prevent excessively large updates, ensuring smoother and more stable learning. This is why PPO is a preferred algorithm for training ChatGPT and other AI models using RLHF. It allows for fine-tuning while maintaining model stability. Reinforcement learning models, particularly deep RL algorithms, rely on neural networks for decision making. But how do these models actually learn? Backpropagation is the key mechanism behind training neural networks, and reinforcement learning integrates backpropagation through techniques like deep networks and PPO. The difference between gradient descent and policy descent is supervised learning. So the model updates weights based on a given loss function, adjusting predictions to match labeled data. However, policy gradient is reinforcement learning, which the model updates weights based on the rewards, adjusting the probability of actions based on how beneficial they are. By combining deep learning with reinforcement learning, modern AI can handle high-dimensional environments, complex reasoning, and long-term decision-making. Traditional LL relies on predefined rewards functions, but human preferences are too complex to encode explicitly. This is where reinforcement learning from human feedback, which is called as RLHF, comes in. Instead of using a fixed reward system, RLHF incorporates human feedback to fine-tune AI models. Here's how it works. First, AI generates multiple responses to a query. Second, human rank the responses based on quality and preference. Third, a reward model is trained to predict human preferences. Lastly, the model is fine-tuned using proximal policy optimization to align these preferences. This method is widely used in ChatGPT to improve the relevance, coherence, and safety of responses, making AI interactions more human-like. RLHF is already shaping the future of AI models by improving their ability to generate high-quality, contextually aware responses. OpenAI's ChatGPT uses RLHF to rank responses based on human preferences. AI models trained with RLHF are used in content moderation, ensuring responses are ethical and unbiased. RLHF is also improving personalized recommendations in platforms like YouTube and Netflix. By integrating human alignment into reinforcement learning, AI can become more trustworthy, controllable, and adaptable to human needs. Despite its success, reinforcement learning still faces major challenges. First part is sample efficiency. So RL models require massive amounts of training data. Second is exploration problems. Agents sometimes struggle to find the best strategy. Last part is reward designing complexity. It poorly defines rewards can lead to suboptimal behaviors. Recent research is addressing these issues with the first part, word models, where AI builds an internal understanding of the environment to reduce data requirements. Second is meta, which enables AI to learn from past experiences for faster adaptation. Last part is multimodal RL, allowing AI to learn from multiple data sources, including text, images, and audio. Reinforcement learning and RLHF are redefining AI from chatbots to autonomous systems. The future of RL will focus on better sample efficiency, ethical AI alignment, and more interpretable models. As AI continues to evolve, RLHF will play a key role in making AI more human-friendly, reliable, and safe. All right, that's all for you today. Thank you for your time.